We're going to continue in chapter 13, hammering away on that. If for some reason that you're commuting far enough tomorrow and you can't make it to lab, send me a picture of yourself under the conditions, and I'll excuse that. So I don't want anybody to have to drive through a nice storm to try to get here to lab. So I know ECU made the call to cancel classes. Some of the other institutions around Southeastern, since we're in good shape today, so far, the institution hasn't, so I can't tell you what the weather's going to do this evening and tonight, but right now, everything's still on go. Yes?
How is
This afternoon, 4:15. It's not 4:30 like it used to be. It's off a little bit. Now, with that said, the blood drive came from Ardmore. I don't even know if they made the trip over, because Ardmore is getting weather that we're not. I mean, it's below freezing in Ardmore. Are they over there this morning? Okay. I would say it's very possible they would go home early today, instead of waiting. I mean, the big thing for them is they want to be back over there before the sun goes down and temperatures are going to drop substantially. Therefore, their driving conditions can get a lot worse. It takes them, when the blood drive quits, it takes them about an hour to pack up, get all the equipment in the trucks and the vans and trailers, and another hour of commute. So I doubt they stay open till 4 today. That's my guess, but I think there. Anything else? Okay. I was happy to see several of you go donate. How many first-time donors today? Just one, I know. Okay. Thanks. The rest of you, I saw a lot of you are there, so that means you donated before. Thank you for supporting that. And I'll just tell you a little bit about my personal resolve on giving blood. I took care of an individual that was a retired faculty member the last 3 years of his life. He didn't have any children, so him and his wife had asked us to help take care of them. He developed leukemia in the last 9 months of his life. We had 12 blood transfusions in those last 9 months to keep him alive. Every time he got between 2 and 3 units of blood. Somebody doesn't make that sacrifice, lay on the table, give a blood transfusion, people die every day. So whether it seems something, I know a lot of people have phobias of needles. You may get a bruise on your arm. You may not get to do something for a few hours, but it's really something small you can do that directly influences somebody's life for a positive. So thank you for doing that. All right, so we're looking at solutions, and we were talking about the types of intermolecular forces and how they relate to each other. So we want to start thinking about the attractive forces between the different types of particles in the solution. So there are 3 types of interactions we have to consider. There's the solvent-solvent interactions. So if it was just the pure solvent, what are the intermolecular forces there? There are the solute-solute interactions, the minor component. If it's just that, what are the forces between them? And then the third are going to be the new interactions between the solvent and the solute as the solution forms in the system. And we have to think about the energy involved with each of those. So there are some predictive things that we can do to say, yes, a solution will form. If the solvent-solute interactions or attractions, intermolecular forces is the best way to describe it, if those are greater than the solvent-solvent and the solute-solute, it's definitely going to form a solution. If the solvent-solute interactions are equal to those of the solvent-solvent and solvent-solute, it's going to form a solution because of the mixing process. The spontaneity that occurs whenever the entropy decreases, going from an ordered state to a disordered state. All right, and then the one that becomes more of a question for us is the solvent-solute interactions are less than the others. So it may form a solution, it may not. It depends on how the order comes to play. It comes down to the difference in the energy that's going to occur, and is that going to be enough to overcome by the increase in entropy that's formed upon mixing. So all those attractive forces start to play some type of a role, and we have to think about the attractive forces that are there and all the different ones that we talked about. The dispersion forces that happen with anything or with all types of molecules or even atoms. The dipole-dipole for things that have permanent dipoles. The super dipoles, those groups that have the hydrogen bond that can form. And finally, the most powerful of them are the ion dipole intermolecular forces that we can have. So you can have any of those types of intermolecular forces in the solute, in the solvent attractive forces, but both of the processes are endothermic. Now, why is it endothermic? Because we have to take those components and pull them apart. Okay, so that's going to require some energy be pulled into the system to do that. But when we go the opposite, the solvent solute, because we're making now new types of intermolecular forces that weren't there, it's exothermic. It's going to release energy off to the system. So the chemist rule of thumb for will something dissolve or not, the rule of thumb is like dissolves like. Polar compounds dissolve in polar solvents. Nonpolar compounds dissolve in nonpolar solvents. Things with a lot of CH bonds dissolve in things with a lot of CH bonds. Okay, so we look at similarities between the structure and the solvent and see if they match up. But if we can look in terms of the intermolecular forces, in terms of does it have just dispersion forces, then it will dissolve in solvents that just have dispersion forces. Does it have polar bonds? Okay, then it will dissolve in solvents that have polar bonds. So those are the types of properties that we try to look at when we try to choose a solvent for a system. Our number one choice for a solvent is always water because of its availability and it's environmentally friendly. But a lot of things won't dissolve in water, and we have to figure out what plan B is going to be in our systems. So solubility is defined as the maximum amount of a solute that can dissolve in a given amount of solvent. And typically we describe this per 100 milliliters or per liter. It can go either way. The limit of, there's usually a practical limit for things that how much it will dissolve. Gases, they don't have solubility issues because gases don't interact with each other. They're just flying by each other. So they don't have to deal with intermolecular forces like solids and solutions do. Liquids that can be mixed at any ratio are called miscible. So that means any combination, you can put them together. Alcohol and water are miscible. Things that you can't mix together are called immiscible solutions. Okay, oil and water are an example of that. Those are things that can't go together in a system. The amount of a substance that you can put in a solution is typically temperature and pressure dependent. If it's a gas, it's highly pressure dependent. How temperature dependent is, it depends on what the intermolecular forces are. We'll look at, for the general rule is, we'll talk about this in a few slides, most things increase their solubility as temperature goes up. There are a few things, because of the energetics involved with the mixing, the solubility goes down. They're actually more soluble at low temperature than high temperature. But that's pretty rare for that to occur. Okay, so if we go to our chemist rule of thumb, like dissolves like, we're looking at similarities between that substance and the solvent, and seeing if those two things are like or similar. Polar molecules and ionic compounds are more soluble in polar solvents. On the converse of that, the nonpolar molecules, the things that have dispersion forces only, are going to be more soluble in nonpolar solvents. When we look at the energetics involved with that, we see different types of heat events occur with different types of compounds. For example, a common thing that we use in the lab is sodium hydroxide. And when sodium hydroxide dissolves in water, it releases a lot of heat. So you take a pellet of sodium hydroxide, you put some water in it, you start stirring it up, you hold the beaker in the bottom, and it immediately gets warm to the touch. You feel it get hot on the bottom. To the point if you dissolve a large amount of sodium hydroxide, like put an inch of sodium hydroxide pellets in it and put a couple inches of water on top of it, it'll get so hot you can't pick the beaker up with your hand. Very, very exothermic reaction. So that's the way sodium hydroxide behaves. But if you look at different types of compounds, so a common thing that we used to use as fertilizer, ammonium nitrate, it's still the compound that's used in Miracle-Gro. Been to grandma's house, she has flowers, she's got Miracle-Gro. Okay, it's the most common fertilizer that you use in a flower garden. It has the opposite nature. So when it is dissolved in the solvent, it absorbs heat from the surroundings and it causes the surroundings to get cold. You can actually take anhydrous ammonium nitrate and put it in a beaker and put a board down on a table and a little bit of water between the board and the bottom of the beaker, pour water in it, stir it around, and it'll freeze solid. You pick it up and the board will stick to the beaker. So it is an example of something that absorbs heat from the surroundings, which is the solvent, in this case the water, to the point that it takes so much heat out it will freeze water from the surroundings. The question is, why does one do one and one do the other? Just a practical effect or thing about ammonium nitrate. So ammonium nitrate can be purchased as an anhydrous compound. So anhydrous means there's no water molecules on it, versus ammonium nitrate that has water complex to it. All right, so it's got n number of water molecules bound to it. And in terms of their fertilizer potential, the two things are equal in terms of helping plants grow. Where it becomes an issue is that the one that's got water to it is very hygroscopic, and it's frequently is almost a semi-solid because of the amount of water that draws into it. Anhydrous ammonium nitrate is free-flowing. It's a dry powder. What became significant after the Murray Federal Building bombing is that this compound, which used to be in every fertilizer farm supply store around, became an illegal substance. Okay, because ammonium nitrate mixed with diesel and set off with a blasting cap becomes a tremendous explosive. It's actually a commercially available explosive called Ampro. We have a number of mines in this area that do strip mining for different types of rock formations. There's a very large one north of us, about 25 miles in the Coleman area. That pit where they take limestone out of the ground, they provide the bulk of the crushed limestone that goes for road formation, but they go almost all of the concrete that's built in North Texas, in the Dallas-Fort Worth Metroplex, the rock comes out of that plant. I live on that road on Highway 78 north of town, 4,000 to 5,000 trucks a day going down that road. It's tremendous volume. Anytime you drive down US 75 during the workday, if you're going the opposite direction, if you're coming northbound, count the southbound trucks that are dump truck style trucks that are carrying a rock to from those crushers. Some are marked Lattimore, some are commercial haulers. It's just a huge volume, but they mix Ampro. They drill holes in the ground that are pilot holes, either 3 or 6 inch bores. They pack it full of this dry fertilizer, and it's in a bag, and then they pour diesel on top of it, fuel oil, put a blasting cap on top of it, and they'll blow off. Typically, they'll do those drills every 10 foot, and they may go back 100 foot deep, so they may blow off 1,000 holes at once, and it will take a couple acres of rock, crush it, then they'll take it out to the mines and start mining it up. There north of this a little bit, there's up by Wapanucka, there's a mine at Bromide, which was also a limestone quarry. And if you ever get a chance to go up there, it's really considered off limits, but it's absolutely beautiful place to swim in. A lot of people, there's a cliff you can jump off of that's about 40, 50 foot up. If you do it, beware the rattlesnakes, because there's a huge number of rattlesnakes in that area. The thing that's bad about that lake is it's so clear, is that you see the bottom, even though the bottom may be 50 foot down. Super clear water. The downside is it looks 50 foot down, and you dive off into it, and it's 3 foot deep. Personal family tragedy. My cousin jumped off of that, broke his neck. So it didn't. He had partial paralysis. He's still alive today, but he lost a lot of function because somebody didn't go down there first and see how deep the water was before they jumped off of it. That changed the fact that this fertilizer, it can be converted into an explosive, changed the availability of who can get access to this versus who can't. And in the farming world, a lot of farmers had to come up with a plan B for nitrogen. They started using urea-based fertilizers and other things that had to replace this. The wet form of it doesn't flow through a fertilizer spreader grease. So the traditional fertilizer spreader a farmer or rancher uses to distribute our broadcast fertilizer into a pasture field doesn't work as easy. We use this stuff for in the United States for almost 100 years, ever since it had been introduced as they were able to make this product commercially, which was following World War I. And we hadn't had an incident where it was used for a terrorism event, but when it was used in the Murray building in Oklahoma City, that changed the nature. And that's the same true of a lot of chemicals that we used to be household chemicals. If they've been adapted and are using things like in drug manufacturing, now they become controlled substances. And you have to have special permits or license to have access to those chemicals. There used to be a lot more chemicals available at the paint store, industrial solvents that we use. Examples of that are chemicals like acetone and methylethyl ketone. Those used to be common solvents to clean the paintbrushes with. They still will sell you a gallon of it, but you can't go buy the 55-gallon drums. And everybody that buys a gallon, the paint store doesn't tell you. They submit your name to the federal agencies that you got this quantity of it. So they actually track where every gallon volume goes with that solvent. So that's just the nature of how chemicals sometimes are used for things that harm the general population and how the government tracks or controls those. Okay, enough of the side story. So let's go back to energetics of putting things in solution. So if we're going to make a solution, the first thing we have to do is we have to break all the attractions between the solute particles. And we call that the enthalpy of the solute, and it's endothermic. It requires energy for that to happen. Second thing is we have to overcome all of the particle or the attractions between the solvent molecules. We basically have to make a hole where the solute is going to go, so we've got to break bonds there, or intermolecular forces. So that's called the enthalpy of the solvent, and it also is endothermic. We look at the new intermolecular forces that are going to be produced as the result of the solute and the solvent particle interacting with one another, and that is energy that's going to be released. So this one is exothermic. So that's the delta H of mixing. So going back to the overall that occurs, is the dissolving of something going to be endothermic or exothermic? It depends on the magnitude of each one of these and how they compare to one another to tell what the enthalpy of the solution is going to be. In some cases, it's concentration dependent. In other cases, in all concentrations depending, when I say concentration dependent, if you had 100 mils of water and you dissolve 1 gram of a compound in it, it may be endothermic. But if you put 40 grams in there, it may be exothermic. Okay, so if it's something like that, depending on how much mixing occurs would be the predominant factor. So just visually looking at these, we have to separate the solute particles and pull those apart so they're isolated from each other. That takes energy to do that. The same for separating the solvent. You have to take the solvent interactions and separate those from one another so you have isolated solvents. That takes the energy for that to occur. but then you form these new new interactions as a result of the mixing of the solute and the solvent. So you have new interactions that weren't there before, so that releases energy off in the system. So the overall becomes, well, what is the relative amounts of energy captured versus lost? And we talked about this type of an energy diagram in General Chemistry 1 in thermodynamics. You start with the isolated solvent and the solute particles. It takes some energy to pull them apart. So in this step 1, you're pulling apart the solute particles, which are represented with green. In the second step, you're pulling apart the solvent particles, which are represented with purple. So you've got those separated. So your enthalpy of solute, your enthalpy of solvent. Once you have them separated, then you take the separated particles, you put them together, and you release energy as you form the new interactions between the solute and the particle, and that's the enthalpy of mixing. So it depends on how much energy is consumed versus how much energy is released in the total. In this example, the drop down was greater than the two amount of energies absorbed because the net is that you're at a lower energy level than you were to start with. So this is going to be an example of an exothermic process. There's a release of energy to the environment. Now the opposite is absolutely true in some cases. So if the total energy required to break the attractions, so the delta H of solute and delta H of solvent put together, if this total energy is greater than that energy that's released by mixing the solution, the net result is it's going to be an endothermic process. It's going to suck in energy from the surroundings. So it's going to get colder. So this is the example of what happens with the ammonium nitrate. So sometimes it's endothermic, sometimes it's exothermic. It just depends on what you're mixing together in the system. Okay, so let's do our first clicker. Two substances are soluble at any ratio, or what? What's the term for that? Okay, I think we're up here. One more. All right, voted, so almost everybody went with choice D, and I like choice D. That means miscible. So things that you can combine at any combination or ratio are miscible, and alcohol waters are a common example of that. But there are a lot of other things that mix like that. Okay, so this one's a little trickier, and I'll let y'all work this one as a group problem. So ask a neighbor. So I want you to answer which one is more soluble in water, or why is chloroform more soluble in water? So I'm telling you that it is, but I want you to work out the why of it. So to really answer this, you have to think about what is the VSEPR structure of each one of those molecules and what's different about them. Okay, and you have to understand that to be able to answer it. So they're very similar. They both have carbon and 4 things attached to them, but you can look at them and see there's some differences. So I'll give y'all 2 minutes to talk about this among each other and then put your vote in. So go ahead.
I know that the will be like balanced, so we can so that it's not what we have.
encourage you to use these opportunities to talk to each other.
So, it's greater than so reaction.
Got 50 seconds.
That's what I'm doing.
You can always change your vote. But if you think you're right, don't get talked into something that you think you're right. All right. 25.
Some days and days. I know that days and they can't right. So they don't have very strong.
Okay. So let's see how we voted. We'll start with that. So most of you went with choice C. Gosh, I hope it's not D. So we'll find out. First thing we want to do to answer this is to think about the VSEPR structure. So both of them are examples of AB4. So they have 4 things attached to the central atom. So carbon wants 4 things bound to it. So chloroform has 3 chlorines and one hydrogen atom. Carbon tetrachloride is almost the same structure, except now they're all chlorine atoms. What's the big thing you notice about difference in structure? Okay, which one's polar?
Other top is the seal.
Okay, so this one has the electronegativity pull towards the chlorine atoms, and it's smaller towards the hydrogen. In fact, it's in the opposite direction. Carbon's 2.5, hydrogen's 2.1. It's going the other way. So this means this has a net dipole moment towards all the chlorine atoms in the structure. Now you still have that same pulling interaction with this one. So why isn't this a polar molecule? Okay, so it's symmetric. Okay, so it's got the same pull all in the opposite directions. And the fact that it's a symmetric molecule, they cancel out. This one is nonpolar. This one is polar. Right? You have to figure that out to go to the next step in answering this question. So once you understand that, you can look at the forces. So the chloroform is a polar molecule. The polar molecules are going to have the stronger interactions with the solvent. In this case, our solvent in the system is water, which is definitely a polar molecule. It can hydrogen bond, but we're looking for the thing that has the most polar interactions. Therefore, it's going to have the strongest solute solvent interactions, and that's what's going to allow it to dissolve most.
Couldn't you say that they attract each other more too, since they're polar?
They do, but if we go back to those rules that will something to dissolve, is that it's not the fact that they have attractions to each other, because the solute has attractions to each other and the water has attractions to each other. It's the new things you can form by mixing. So you have to compare what is the solute-solvent interaction that's occurring. And the fact is it occurring at all, that's not our question, how is it occurring in comparison to this one? When you look at what would the attraction be between the water molecule and a nonpolar molecule, it's minimal. So this energy of mixing is terrible or small. This one would be quite large. I mean, this one would be dispersion forces only tiny, where this one would be very large. That's what gives it the energy to dissolve. I'll ask you, and that's a really critical thinking, because you got to think about structure. There's a lot of things to put together from the previous chancers chapters to be able to answer that. I don't consider that an easy question by any means. I will give you a question like that on this exam. Very probable you'll see a question like this on the final exam too. Okay, so that's just a type of thing you need to understand. Other classes where they're going to ask you things like this, organic chemistry coming up, biochemistry that some of you will take, even if you're going to go the biology tracks. When you get to cell biology, it's all about these types of polar interactions. When they look at something going to occur in that portion of a cell or not, well, what is the environment? Is it a polar environment or a non-polar environment? So understanding these fundamentals go a long ways to take you further in the sciences. Okay, so when we look at what's going on when something dissolves, the dissolving or dissolution process is a fancy word for dissolving of a solute in a solvent is an equilibrium process. So initially what happens when there's no solute dissolved, the process is one directional. It's only in dissolving. But as soon as you have some solute dissolved, some of the solute can start to recombine and reform the solid molecules through crystallization. It's much like what happened with the vapor or the liquid going to a vapor versus condensation equilibrium we talked about in the previous chapter. Same type of thing occurs with solids. So as long as the rate of dissolving or dissolution occurs faster than the rate of deposition, the solute continues to dissolve. But eventually what happens is those two rates are going to be equal to each other. When the two rates have become equal to each other, that's all of the solid that's going to go in the solution. The term we use to describe that is a saturated solution. So there's no more solute that's going to go into the solution at that point. Got the hiccups. Okay, so that point's the most you can dissolve into the system. So if we look at just graphically quickly, if we throw some sodium chloride in water, initially what happens is just the sodium chloride starts to interact, the water molecules react with the ions and the ionic bonds, and the sodium chloride starts to dissolve rapidly. It produces the ions in solution. But once the ions get in solution, some of the ions can recombine, and those ions could come together and reform the crystal on the surface, so you have recrystallization. So that process, if you reach a point where you put enough salt in water, there's only a limited amount, even though sodium chloride's pretty water soluble, you reach a point at about 40 grams per 100 mils, that's the most you can put in. Okay, that's the solubility limit. So once you reach that point, the arrow is not one way, it's two ways. The rate that it's dissolving or dissolution is occurring is the same rate of crystallization, and you reach the point of solubility. So terms that we put are the descriptions of where are you at in this equilibrium. We say that a solution where the solvent and solute has reached the equilibrium, we say at that point it's saturated. And if you have a solution that's saturated, if you add more solute to it, nothing else is going to dissolve. The saturation concentration that occurs is temperature dependent, and if it's a gas, it's dependent on the pressure of that gas. So if we think about what this means, if we took a solution, a beaker, and put some water in it, and we put in something that's not very soluble, and a common compound that we use is silver chloride, because silver chloride has a low solubility in water. So if we take silver chloride and we put that in water, a small amount of it will dissolve and go into the aqueous portion. But it doesn't take very much at all, and it saturates that system to the point that it reaches the equilibrium. The silver and the chloride would start to come back together. So if we put just a small amount, and if we're talking a liter of water, we need a few milligrams of it, and the system will reach a point of saturation where the dissolution process equals the recrystallization process. So there'll still be a few ions floating around in solution of each of these, but not very many. the concentrations of the silver cation, the chloride anion, are about micromolar, 10 to the minus 6. So not very many. Now, once it's reached this maximum point, it doesn't matter if I have one extra crystal in here, or if I take and put 2 more inches of silver chloride solid. The fact that it was saturated, you can't get more saturated. Okay? The addition of more solid doesn't allow any more to go in solution. So as long as you've got even one crystal present, any solid whatsoever in a saturated solution, it's saturated. Additional solid does nothing to help you out at all. Now, if it's unsaturated, if you're not at that point yet where it's reached equilibrium, then the solution has more solute that can be dissolved. So an unsaturated is less than the point of saturation. So more solute will dissolve at this temperature. Now, sometimes we can create solutions that are supersaturated. Supersaturated means that it has more solute than is said to be soluble at that temperature. How's that possible, you may ask? Well, let's talk about how you could create those. So a supersaturated solution is typically made by doing the dissolving process at non-room conditions and typically allowing it to come back to room conditions. Most commonly, we apply heat. So for most compounds, when you apply heat, the solubility increases. So you can take a solute and heat the solvent up instead of room temperature, take water up to right at the boiling point of water, and you maybe could put an additional 20 to 40% of that solute in solution. And then you turn the heat off once it's dissolved and allow it to cool back down. And in some cases, the substance will recrystallize out and it will reach equilibrium. In some other cases that are a little bit more rare, the molecules get stuck in the suspended state, in the solution state, even though it's above the point of saturation. So that's what we call a supersaturated solution. So instead of coming out of the solution and forming the solid, they get stuck in between the solvent and the solution molecules and become this supersaturated state. Now, supersaturated solutions are highly unstable, and when they start to precipitate out, they will precipitate out all of the solute as soon as you disturb the solution. And an example of this is shaking a carbonated beverage. Probably everybody's had the unfortunate experience of your best friend drops a bottle of Coke out of the refrigerator or whatever it is, or the can, and then they switch it back for the one they dropped, or hand you the beer that just shook up or whatever, and you open it up instead of going shh, and you get a drink, you get sprayed by it. Okay, so that's an example where the equilibrium has been disturbed by the shaking or the change in shock, and when you open the pressure up to it, all of the gas comes rushing out. That's nothing can make you matter. So sometimes it happens on accident. Sometimes it's a malicious trick, and it can be funny if you're doing it on somebody else, but you don't see the humor if it's done to you.
So does it lose everything, or does it
To the point of saturation.
Okay.
So it goes back to the point of saturation. One of the neat demonstrations that we do with this is with that of crystalline sodium acetate. So the solubility of sodium acetate is highly temperature dependent. So we usually do this with a beaker in a demo in class. The problem is your beaker has to be completely scratch free, and you need to make it up and not move it. So all of our classrooms used to have sinks and stuff in them, where we had classes smaller and we could do demos in class with a demonstration table. Now we're trying to get as many students in the class as we can. We don't have that available in this room. I can make this up in the lab next door. Maybe 50% of the time I could bring it over here hot, put it on the table, and it would stay in solution. The other 50% of the time, just the movement in it causes it to form a crystal. But you can take a supersaturated solution, heat it up till it becomes soluble, and I can drop one crystal of this sodium acetate into it, some solid, and that seed crystal starts the crystallization process, so that in a matter of literally 2 to 3 seconds, it starts to form these growing crystals out of it. And in a matter of, at the end of 3 seconds, it's solid all the way through. That's pretty cool to see that. You can watch YouTube videos. There's a bunch of them out to look at the supersaturation of sodium acetate, and you can see it happen in real time. It's a neat demo to watch. All right, so we want to look at how things are temperature dependent. If we look at the temperature dependency of solids in water, typically we describe how soluble a solid is in terms of the grams of the solute that dissolve in 100 mils of water, and water has a density of 1, so it's 100 grams of water. Most commonly what happens is that the solubility of the solid increases as the temperature goes up. You want to dissolve something, you apply some heat to it. That's true when the enthalpy of the solution is endothermic, so it needs to absorb energy to go into solution. If we look at the solubility curves, they can be used to allow us to predict whether or not if something is going to go into solution or not. So if we're below the point of saturation, it's going to be soluble. If we're at the point of saturation, it's still going to be soluble on the line. We just can't go beyond that and add any other. So we have to determine sometimes is the solution at the point of saturation, is it unsaturated below the line, or is it supersaturated above the line? So here is the example for many different compounds, and each one of them has a different color associated with it. Look at most of the trends. The trends are, and I'm just going to mark towards the end, that most of them have an upslope. They're going up as temperature increases in the system. So all the ones that I've marked there do. Now, some things are not as temperature dependent. For example, sodium chloride only changes its solubility a few percent, going from 0 degrees to 100 degrees. It changes from about 33 to right at 40. So that's a 15% change, roughly. But you look at something different, like the example potassium nitrite, it goes from 15 grams to above 100. So you can put more mass of that solid in there than you put water in it, and it'll still dissolve. And that occurs only down at 50 degrees. The rarity that occurs are things like the cerium sulfate. So it's one that has a negative temperature dependency. So the more you heat it up, the lower the solubility becomes. So it's an example of something that would be very exothermic in terms of energy that's getting off. When you put heat to it, it's driving that mixing in the opposite direction. So one of the questions that we'll look at is you simply need to know what is the solubility at a given temperature. So we may have a graph like this on a test, and I'd say that at 10 degrees Celsius, I'm trying to dissolve 25 grams of calcium chloride at 10 degrees Celsius. And I would want to know, is it soluble? Is it saturated? Or would that be an example of supersaturated? Okay, so soluble would be, it's at the point of unsaturation. So which one would it be? Well, I find the sodium chloride or calcium chloride line, and I go to 10 degrees, and then I would find out where I'm at. So if I'm putting 25 grams in, it would be right here. Well, the line for the solubility limit's way up here at 60 plus grams. So this would be an example where it's unsaturated or soluble. All right? It's as simple as that. If it's on the line, that means that it's the saturated case. And if it's somehow above the line, so let's say that a system that had 70 grams of calcium chloride in 100 mils of water at 10 degrees, what would it be? It would be an example of supersaturated, okay, because you're above the solubility limit in that case. I'll ask you something like this on an exam question. Okay, so if you'll look at the old exams, I'll give you one of these curves. It may have several compounds on it. It may have just one compound. but I'll ask you to tell me something about the state of something. Is something soluble or is not, or what is the state? Or maybe read the graph and tell me what the solubility would be at a given temperature. You'll have to answer something dealing with one of these graphs. All right, so here's the first example of that. So a solution contains 25 grams of KCl and 100 grams of water at 50 degrees. So I want to know what's the state. One more. All right, roll in. Most abundant choice is choice B. One person went with A, one person went with C. So we got to figure out where we are in this thing. So our substance is KCl. So this is the line we're looking for. And the temperature is 50 degrees. So I would go up at 50 degrees to see where we are on this. And it tells me that we have 25 grams and 100 mils of water. So I would go over at 25 grams and be seeing where I'm here. At this point, I'm below the line for the limit of solubility. So that is an example of an unsaturated solution. Okay. If it were on the line, it would have been choice C. So if it would have been right here, this would have been choice C. If it were anywhere above this line, so anywhere in here, this would be the supersaturated choice A. Okay. All right. We conquered solids. Let's look at what's next. And the next is looking at a common technique that we used to purify solids, and that process is called recrystallization. So a lot of times we make something in the lab and we end up making more than one component, or we have impurities in the parent chemicals that we use, or the solvent. There's a lot of ways to buy chemicals at different levels of purity. Just to give you an idea on purity, what we typically call technical grade chemicals are 95% pure. The 5% is something else, right? Sometimes purity is not an issue. It doesn't matter what that 5% is. What we commonly call ACS grade chemicals are chemicals that are 99% purity. And then when we go to high purity chemicals, you're typically 99.9. To give you ideas on how much that differs in cost, something like a common compound you might use like benzene. Benzene technical grade is a few dollars a kilogram. All right. If you go to the ACS grade, benzene now costs about $50 a kilogram to get it 99% purity. And if you want 99.99% purity, now you're talking about $20 to $30 a gram, not a kilogram. The high purity has a significantly high cost for it. That's one of the things that in the pharmaceutical industry, we have to be certain the product that we're giving the patient, or if it's going to an animal for the treatment of animals, that it's high purity. And the amount of the content of that particular, whatever that dose of the medicine is, whether it's a shot that's given or a tablet or a capsule, its content has to be known with a high degree of accuracy. Knowing that the continuous quality control causes a tremendous cost to the expense of manufacturing pharmaceutical compounds. There's a big discussion now, why does insulin cost so much? I'm a diabetic, so to me, at some point, I know as a type 2 diabetic, I'm taking pills that control my blood sugar right now, but at some point in life, I'm going to reach a point like everybody else does that's type 2. You're going to be on insulin. Either that or you can choose to lose weight and get in shape, and that hasn't happened yet, so I'm not expecting it to happen in the near future. But using exercise, I can control mine at this point. But at some point, your body's and the pancreas's ability to make insulin slows down as everybody ages. Almost every type 2 diabetic reaches a point where they become insulin dependent. So that's my future. I'm not blind to that unless I change my lifestyle. But the thing is the cost of insulin. Some states around us recently have passed laws that put a cap on how much an insulin pen could cost, or how much. And the part of the expense with insulin is the convenience. A pen that you use costs literally like a Homolog pen, which is a type of brand of insulin that's a certain mixture of time-released insulin. Each one of those individual pens, if you pay for it out of pocket at Walmart, it's about $500. All right. Insurance even covers it. They're still down or about $100 still. Tremendously expensive, and that's maybe a week's worth of doses, depending on how much you're using a day or per most. It depends on the type of diabetic you are. Some people have to wear a monitor, and if they're typically type 1, they're so insulin dependent that they have to wear a pump, and they'll wear a patch on their arm that continuously monitors what their blood sugar is. Today, the technology is it hooks to your phone, and you're wearing a pump that automatically pumps insulin into you to maintain insulin. That's probably the future of diabetic drug treatment. But right now, almost no insurance is covered for that. You got to pay for it private pocket. However, if you want the most normal life, you pay $5,000 for the technology, and you can live a very normal life. But if you take the bottle of insulin, turn it upside down, pull the needle out to the right amount, and give yourself a shot, the cost of the insulin goes down by a factor of 20 versus having the pen that you dial in. The same is true of an EpiPen. Epinephrine is not expensive. The EpiPen and the technology of the pre-measured pen, the technology is what's patented, and it costs a lot in Japan. So those are issues that maybe the government has to work out. But going back to the insulin story, there was a problem where we were importing insulin from China 2 years ago, and that insulin was very contaminated with something other than insulin. And about 100,000 people got some poison from the other proteins that were in that pen besides insulin. Insulin's a protein. That's one of the things with quality control. You've got to go through a lot of steps to make sure it's a sterile environment, that only the things that are going in there to create that chemical compound are there. The former company I worked for a company called Monsanto in St. Louis. I was at their corporate headquarters before I came back to Southeastern to teach. We had a pharmaceutical company. Cyril was our pharmaceutical company. It was bought out by Merck in 2001, but I constantly dealt with things that were submitted to the Food and Drug Administration, and there were a huge amount. To take a new potential drug to the stage of human testing took $2 million in the 90s, early 90s. It was extremely expensive just to try to see if something worked. When you take a compound and go through all the clinical testing to the time you do the initial R&D to make that drug to the time, I mean, the companies have $20-30 million invested in them. And the success rate is about 3%. Okay, so about 3% of the compounds that they say this is going to be the drug for the future actually make it to the market candidates. The rest of that is wasted R&D. Okay, and that's part of the hit that we don't realize it on the back end as consumers. That's part of what we're paying for when we want our pharmaceutical compounds. Now, is it cheaper to buy your drugs in Mexico or Canada? Yes, because they're not under the same patent restrictions as the United States. They're just taking what some other company invested in. The quality of those drugs may not be the same in terms of purity, but those countries are not producing any new drugs for you. So they're not investing in any research and development to produce the new product that's going to help cure cancer or whatever the next thing is that we have to cure. Right now, if we need a protection for the coronavirus, pretty bad, and we don't have any protection for that virus other than isolation. So how are we going to deal with problems like that? All right. Purifying our drugs, the common way that we do it is we will take and remove impurities from a solid compound, and we do that by dissolving it in a hot solution so it becomes super saturated. We'll allow the solution to cool down, and it crystallizes the solid out, and it leaves the impurities behind. So when the crystallization process starts in a supersaturated state, the crystals will form with compounds that are the same solute. So if you had two things that were dissolved in this solution at a given temperature, if you had A and B in solution, if it starts to make crystals of A, only molecules of A would bind to that crystal and B would stay in the solution. Right? Now, that works well with things that form unique crystals like these. You can see the crystalline shape associated with this compound. Not everything forms a crystal. So some solids are what we call amorphous, some are crystalline. Crystallization doesn't work for everything, and it typically will only increase the purity up to somewhere in the neighborhood of the upper 90%, certainly not at the decimal place. But if you have something that's 50% pure, taking it from 50% to 95, that's a huge step. Okay, and that may be good enough for what you need to do. Okay, so switch gears and we'll look at gases. So if we look at the temperature, solubility, or dependency of gases, it's a little different. So what happens is gases in general have a lower solubility in water than what can happen with ionic or polar compounds. And the why? Because most gases are nonpolar molecules. Not all of them, but most of them are. If we look at things that have a very high solubility in water, they're usually actually the result of reacting with water. And I'll give you an example of one of those, which we've used this semester already. If we look at ammonium, NH3, NH3 is a gas, dissolves in water by reacting with a water molecule, and it transfers the proton from the water molecule to form the NH4 plus cation. And then when you take the water molecule or the proton from water, it forms the hydroxide, and those two things pair together to make ammonium hydroxide. So saturated ammonia gas in water becomes ammonium hydroxide. You can actually dissolve ammonia up to about 27% by mass. Right? Hydrochloric acid works the same way. There's a lot of these small compounds that they exist in solutions as a result of a reaction with water to form something new. Okay, for all gases, the solubility of the gas decreases as the temperature increases. And the why of that is the enthalpy of solution is exothermic because you don't have to overcome the solute-solute attractions that you do with solids and liquids in solution. So if you're a Diet Coke fanatic like I am, you know that if you keep your Diet Coke in the refrigerator and you pour it into a glass, not near as much foams out. But if you have a warm soda and you pour it in your glass, much more of the CO2 comes bubbling out, foams over the top. Okay, so if you want to get the most CO2 in your glass with your ice, or the most soda in your glass with the ice without overfilling it and running out, you put your 2 liter in the refrigerator, pre-cool it. It'll also keep your ice there longer. All right, if we look at what happens in a gas, going back to the example of a common thing we use, the CO2 dissolved with the soda, the larger the partial pressure is of that gas that's in contact with the liquid, the more soluble that gas is. So if you take a soda can that's a carbonated beverage, what happens is they make this substance up, and then under high pressure they expose it to CO2, it dissolves the CO2 into the solution. And as long as the can is closed, the CO2 stays dissolved in that solution. But the moment that you release the pressure off the top, you pop the top, the CO2 comes flying out of the solution. And you know what happens if you leave the lid off the Coke bottle for the day? All the CO2 is gone. It becomes flat. All right? So that process will occur pretty quickly, and the more that you disturb it, the quicker it will occur. If you take a Coke and you pour it into a cup, all right, and just take it and pour it back and forth between 2 cups and do that 20 times. And you can do that in a minute. And you take a drink of it, it's as flat as it can be. Okay, because you've disturbed that system and you're allowing the gas to escape every time you pour it back and forth. If you want to keep the CO2 in it, make it a carbonated beverage, you have to keep it under compressor and controlled system. How much of a gas is dissolved into a solution is described by Henry's law. And Henry's law says the solubility of a gas is directly proportional to the partial pressure of that gas. So we have a formula that says the solubility is equal to the gas constant, K sub H, we call that Henry's law constant, times the pressure of the gas. So if we look at the table that's in our book, this is 13.4, it gives you some comparisons for some different gases, and you'll see that these values change a lot. Now, K sub H has units of molarity per an atmosphere. So that means the partial pressure of the gas needs to be in atmospheres. All right, so if it's in millimeters of mercury or something else, we've got to convert it to atmospheres to do this calculation. Okay? All right, so if we look at how much it changes, usually for things that are not polar, this number is 10 to the minus 2, 10 to the minus 3, something like that. Helium, 10 to the minus 3. For things that like ammonia that will react with the substance, it can be quite large. So it's actually 58 for ammonia, but it's because it reacts and makes the ammonium hydroxide. Much, much larger than the others. The gas that's a little bit different, CO2 is a nonpolar molecule, but because it can form an induced dipole, it's significantly larger than these other diatomic compounds. So just looking at which one is most soluble gas, which one is the most soluble in water, comparison of CO2 or O2, I'm looking at the one with the largest constant. So O2 is 10 to the minus third, CO2 is 10 to the minus 2, so CO2 would be the one that's most soluble in water. Whatever has the largest magnitude of the K sub H is there. So the solubility is simply going to be K sub H out of the table times the pressure of the gas, in particular the partial pressure of the gas. It doesn't matter what the total pressure is. It matters what the partial pressure is for that gas that's dissolving. If you have a mixture of gases, each one of those gases will dissolve to some extent, depending on what the K sub H is. When it does dissolve, the units of how much it dissolves is going to be molarity, moles per liter. Yes?
So if you put 2 different gases in there, would they still dissolve the same amount as if they were put in just one gas?
They would, depending on what their partial pressure. So if you had, that's a good question to ask. Let's explore that. So let's say that you had some water in a pressurized container, and you put in 3 atmospheres of nitrogen. It would dissolve at a certain rate in the nitrogen, okay, depending on that partial pressure. Now, if you added to that another 2 atmospheres of oxygen, the oxygen would dissolve down to solution, depending on what its K sub H is, completely independent of the nitrogen. Because what matters is the partial pressure of each gas. So it matters on the partial pressure of the dissolving gas. Now, if the total pressure changed, if the total pressure is still 3 atmospheres, and you have a mixtures of gases, that means that 3 atmospheres is going to be divided between those 2 gases to some extent. They both can't be 3 and 2 and have a total of 3, so then it would decrease. But if the partial pressure stays the same, the solubility stays the same. That's the way we think about that. Okay, here's the example of a couple of things that dissolve in water, and those are common things. So oxygen dissolves in water, CO2 dissolves in water. CO2 dissolves at a much, much higher level. So we can put, if we go to a partial pressure of a couple of hundred atmospheres, we can put a tenth of a gram of CO2 in water, but oxygen's there at a much, much, much lower extent. And that's reflected in the difference of the case of H. So the slope of this is what the case of H, the value is. So we think about what we're seeing in this. The slope of the curve is equal to a function or dependent on the Henry's law constant we talked on the other page. So the slope of in this case, the CO2 versus the slope of the O2 curve that we had on this one, much flatter. And that reflects less of that gas going into solution. Okay, so that's a pretty straightforward calculation to do. You've got that the solubility is equal to K sub H times the pressure of the gas. So I want to know how much O2 is in water at 25 degrees if the pressure of the gas, the O2, is 1 atmosphere. Okay, so you know you can look up the K sub H in the table below. You can look up the partial pressure of the gas, or you're provided the partial pressure of the gas. So just do the calculation. Last 3. All right, so got the last one in. So almost everybody went with D, and I like D as a choice. Okay, so this one's the super easy one because it's at 1 atmosphere. The solubility is just equal to K sub H. So you go find the substance, it's O2. So it's 1.3 times 10 to the minus third. And the units are molarity per atmosphere. And in this case, the pressure is exactly 1 atmosphere. So all you have to do is cancel the units out. The solubility is equal to the K sub H value. If it were something other than 1 atmosphere, it could be less than or could be greater than. You just multiply it by the pressure. But this one's just a simple example. Okay, so want to talk a little bit about, we talked about on the previous graph, that CO2, okay, what's in the blue line, has a much higher solubility under pressure. So this is the story of Lake Nyos. And Lake Nyos is in Cameroon, West Africa. So it's over here on the eastern side, or the western side of the continent. And it is the Lake Nyos is a volcanic lake. It's got a little bit of altitude. It's up to a few thousand feet. But as a result of this volcano, It's a very deep lake. It's not a huge, large surface area, but it goes down to several hundred feet in depth in this small volume. And this lake that had been sitting there quiet for several hundred years, on August 21st, 1986, burst out a cloud of carbon dioxide. So literally, just huge bubbles came from the bottom of the lake. As the result of it, 1,700 people died and over 3,500 head of cattle. Okay, so why would this happen? So, I mean, here's the entire lake. It's small. When it turned over, what happens is that one of the major gases that is emitted from a volcano and is trapped in volcanic rock is carbon dioxide. So the CO2 was slowly seeping out of these rocks, but because it was going into this gas at such depth, as you go deeper and deeper into the depth, the pressure builds up higher and higher. So the pressure the solubility kept increasing till finally it reached a point where all of this gas in here became super saturated. Something disturbed the bottom. It may have been a slight earthquake, a tremor, or something, and all the CO2 come rushing out. Now the problem with CO2 come rushing out is that CO2 gas has a molar mass of 44. The air that we breathe is composed primarily of nitrogen and oxygen, but they have molar masses of 28 and 32. The one that's the heaviest stays on the bottom. So what it did is made about a 50-meter thick layer or river of CO2. Invisible gas flows down the river. People are suddenly suffocating. There's no oxygen. And it killed 1,700 people. That's a pretty freaky thing to happen in nature. But they know what happened. The way that they overcame and prevented this happening again is they just installed a few pumps that pump the water from the bottom of the lake up to the top, spray it out, allow the CO2 to escape. Simple solution. We just didn't know there was a problem until it killed 1,700 people. Okay, so that was kind of an oddity of nature to see something like that happen. It certainly has happened many times in the past in other places. This is just the first time we documented the unique thing like this going on. All right, so we're going to pick up with concentrations, and concentrations are how we describe solutions that have durable composition. You talked a little bit about this in Gen Chem 1, in one of the chapters. I encourage you to look at this stuff ahead, so we're going to stop there today, but review this section of the notes. The stuff that we're going to go over in the next 20, 30 slides is critically important to your future chemistry, because every class that you take beyond this, you're going to have to make solutions of a certain concentration. You have to know how to do these calculations. Okay, so to review that, we'll start back on this on today's Wednesday. Start back on Monday. All right. With that, I'll see you in lab tomorrow. If you of you still haven't finished the Master of Chemistry, finish it up. You still get most of your points if you do it tonight.